Hello everyone. I'm super excited to be speaking here today. It's an incredible lineup of speakers that this conference has assembled. So congrats, of course, to everyone who has been involved in organizing RedisConf 2016. And of course, to all of the speakers as well. This has truly been tremendous. Today, I'm going to be talking about how Rocket Fuel leverages the power of Redis cluster to validate billions of events on a daily basis. I'm going to be talking about the initial problem that triggered the adoption and initial usage of Redis cluster within our tech stack, and how that has gone to and evolved within a short frame of time to handle increasingly complex services and at a tremendous scale. I'm going to be highlighting the tight latency requirements of some of our services and at the scale at which they operate. But more importantly, I want to highlight how by making some very simple optimizations on your client side, you can achieve some very impressive numbers on your Redis cluster. At the same time, I want to shed some light on our cluster setup details and how we handle alerting and failure. And over the course of this session, I hope to paint a picture of one of the many ways in which Redis can be used, and I hope that this triggers in the minds of the audience present here today, and also those watching online, on how similar problems can be solved within their domains. But before that, a little about me. My name is Rahul Varma, and I hail from a city known as Bangalore in India, also known as Bengaluru now. I completed my bachelor's and master's in computer science and engineering from Indian Institute of Technology, Kanpur, and I currently work at Rocket Fuel. Not this one, but this one. I've been at Rocket Fuel since 2013, which makes me one of the old-timers here. And I've been working in the serving infrastructure team, which is responsible for handling all of this incoming web traffic that we see. So let's dive into the talk. This being a business use case presentation for Redis, I understand that there is a segment of the audience which is more keen on understanding the specific nature of the problem that is being solved using Redis. And at the same time, I'm sure there's a segment of the audience which is more interested in the infrastructure setup and how we perform alerting and handle the various failure scenarios and so on. I will try to keep this in mind, and over the course of the talk, try to cater to both segments of this audience. So initially, I'll start by describing some impressive numbers that we see on our Redis cluster, and then I will move on to the problem that we are trying to solve, and then finally wrap up and conclude by the infrastructure setup that we have in place to achieve the kind of scale that we are looking at. I want to start off by showing you right off the bat 4 statistics. And all of these statistics are from a time frame from April 1st to July end of last year. The reason for choosing this particular time frame is that this time frame is very indicative of how rapidly our cluster has evolved. And also by having all of the metrics on the same time frame, you can get a very holistic idea of which metrics are changing and how these metrics are changing. The first statistic that I want to show you is operations per second. If you look at early April, we are looking at close to 200K QPS per second. And this goes on to become not 5, 6, but 7 times and exceeding 1.5 million operations per second by the end of July. That is a span of 4 months. And I haven't mentioned, this is just a single cluster. And we have 7 such clusters, one on each of our data centers across the globe. You might wonder what our latencies are with that kind of operations per second. We're looking at around 1 millisecond latencies in the early part of April, and this goes on to increase naturally because we have much more complex services running by the end of July. And close to the end, we're looking at close to 2 milliseconds, sometimes touching 2.5 during spikes. And that was 95th percentile latencies. Perhaps my favorite graph is the 99th percentile. Why I like this graph is because I've worked with a lot of distributed systems and services, and I've seen some very impressive numbers to say 95th percentile, sometimes 96 and 97. But beyond that point, they start showing steep degradation. I'm sure some of you have worked with services of that nature. And by the time you're looking at 99 percentile values, these are really off the chart, sometimes an magnitude of order higher than 95th percentile values. And here we can see that our 99 percentile latency values that we see on our cluster have been within 3 to 8 millisecond and very acceptable for what we are doing. Memory usage. Very interesting graph, because if you remember, the operations per second just were out of the roof, right? They scaled up to like 5 to 6 times. Memory usage, on the other hand, did not go up. This can be attributed to two facts. The increasingly complex services that were added later on this cluster were more read-heavy. But that's just one part of the equation. The other part is this can be attributed to a lot of memory optimizations that we did during this frame of time, because we had to add all of these services. And by keeping this memory in check, we were able to scale to these numbers. In fact, if you notice, there is a fall beginning April towards mid-May. And that can be attributed to memory optimizations that we have done. And these are not complex memory optimizations done upon top of Redis. It's not like we've added a compressed data structure to the already awesome set of data structures that Redis provides you. But this is just being critical of what you're putting into Redis. Do you need it? Examining the TTL for all of these IDs that you're storing, and so on and so forth. Now, having covered the metrics, I want to move on to the problem. To understand the problem that we are trying to solve, you need to first understand what Rocket Fuel does. Rocket Fuel is a marketing technology company which takes part in RTB, or real-time bidding auctions, on behalf of our clients to show the right ad to the right user and at the right time. We do this using our proprietary moment scoring technology, where we churn the rich behavioral and interest data for all the internet users across our machine learning-driven models to optimally score every auction opportunity that we get. This graph is a very good representation of the scale at which we operate. We are looking at anywhere from 1.5 million requests per second up to 2 million requests per second. Each of these requests is a web auction request and needs to be responded to within 100 milliseconds, or the blink of an eye. Each of these requests, that's the SLA. You have to respond. But if you don't respond, you do not get to take part in the auction. And each of these requests, in turn, is very rich with information. You have information about IP address, the site context. You have user agent information and the customer ID. And all of this helps us get a very clear understanding of the user who is landing on the page. The customer ID is kept in sync with the auction partners, and that helps us know all of this available online history of this internet user and help us understand what would be the right ad for this person. But we need to do this within 100 milliseconds, of course. This summarizes what our platform looks like, and along with the ecosystem. We have a user who lands on a web page. Page request is generated, of course, to the servers of the publisher. And they then, in turn, hold a request to the auction platform, which is forwarded to us in the form of a bid request, which we saw in the earlier graph. Rocket Fuel then uses its big data and machine learning, along with the moment scoring technology that it has in-house, to show the right ad and respond with the right bid. The bid needs to be right so that we are able to optimize on what we are showing and how we are using our resources. That finally, if the auction is won, gets shown on the user's page along with the web content that he was accessing. And then the user may choose to engage with the ad, and that will result in more data. Briefly want to touch upon a few terminologies that might be useful during the course of the session. A bidder. Bidder is what we commonly refer to for the backend server, which is responsible for handling all of this incoming web traffic to our data centers and to responding to this traffic with the ad. So that is the responsibility of the bidder. RTB is an acronym for real-time bidding and is indicative of the nature of the way in which ad slots are bought and sold today online. Redis is a data structure. Okay, I probably do not need to do this. I'm just kidding. Some numbers to crunch. These numbers will come in handy when we try to do some back-of-the-envelope calculations later on during our talk. The total number of bid requests that we receive, close to 120 billion requests on a daily basis. 120 billion, yes, with a B. And that amounts to close to 2 million queries per second during peak hours. But that is global traffic. Now we need to be concerned with more so of the data center level traffic, and we're looking at about 35 billion requests at, say, 500K QPS. Each of these auctions can be chosen to respond to, or we can choose to skip it. The bids is the number of auctions we respond to. Total number of bids we make is, of course, going to be a fraction of the total number of bid requests. The denominator of the equation may be anywhere ranging from 1 to 10, depending on how aggressive we are or how we want to go about our resource management, be it time and money. Wins are all of the auctions that we win. And this, of course, is going to be a subset of the total number of bids we take part in, which in itself is a subset of the total number of bid requests we receive. So this usually in all of our equations that we'll be doing gets overshadowed by either bids or bid requests. So how do we use Redis at Rocket Fuel? We use Redis internally for a lot of our services, especially ones that need to store transient or rapidly changing data. And these services would make for an interesting session by themselves, I'm sure. But today I'm more interested in talking about how we use Redis cluster, which is the hot topic for today. And we use Redis cluster to build what we internally call as the event tracker. So what is the event tracker? The event tracker comprises of a Redis cluster, which acts as the backend data structure server. And built on top of this is a collection of high-performance services which are tracking various events in real time. These events are happening during the bidding loop. Every bidding loop, as you remember, would be an auction is created, we receive the bid request, do our magic, respond to it. And during these times, there are several events happening, and we might want to track them. Now, let's say we might want to add a new service to the event tracker collection, and that results in at least a total number of bids increase in the total number of operations that are happening on this cluster. And that is understandable because every time you make a bid and you're trying to track an event within the bid, you're going to hit the data structure server at least once, if not multiple times. So if you hit it multiple times, that will be an increase would be seen an order of multiple of the total number of bids. And in this session, I want to discuss how we track one such event, which is perhaps the most important event, and is also simple enough to be covered within the scope of this session. And that is the auction win. So what is the auction win? Well, auction win or the bid win, as the name suggests, is when the bid that you've made qualifies as the winning bid, and you get to show the ad. This event is known as the auction win. Why are auction wins important? Auction wins help us get a sort of a feedback loop. What kind of feedback loop? Well, let's say you have campaigns, and these campaigns have goals. Let's say your goal is to show 100 impressions on this campaign today, 100 ads, right? And when you win an auction and you get to show the ad, you want to increment relevant metrics surrounding this so that you know in real time how much progress you have made. At the same time, you might even want to check for some discrepancies or fraudulent behavior. Discrepancies could be in the nature like, have you paid the amount that you're willing to pay in the bid that you have mentioned, or have you ended up paying more? Discrepancies like these are rare, but are very important for us to keep track. So how do we accomplish this? Well, the solution is not too difficult. we can fire a notification from within the ad that we choose to show to this user. That will come back to us with all of this relevant information from the client's browser. We will get the information like the bidding price, the site that we're showing the ad on, and the ad ID which was finally shown. So all of this information then comes back to us, and then we can validate, is this what was expected? Are we on track? And can make some changes on our real-time delivery management. Okay, I've made progress so far, and I still need to go so much to achieve the goals for today. So where does the win notification lie in all of this? Well, as you realize that the ad is shown to the user in the arrow 8, and right after that, we have this red arrow representing what is the win notification. It captures all of the feedback that we need, the information that we need, and comes back to us. So this is what our bid flow would then look like. This is, of course, a very simplistic model of all that is going on behind. You have a bid request, it hits the bidder, Rocket Fuel decides to make a bid, the ad is shown, we update real-time metrics. Success, right? But do you see what is wrong here? Well, the problem with this solution is that this is very simplistic. This is good in theory, of course, it will work, but it fails to account for all the things that can go wrong in a real-world scenario. And what can go wrong? Well, you have bots out there. And by bots, I mean just any non-human web traffic and not something like you would see in Terminator 2. But any kind of non-human web traffic, say even something as simple as a for loop inside a bash script would constitute as bot in our case. And let's say this for loop is requesting the notification that you mentioned in your ad several times. Well, everything breaks because the bots will fire the pixel several times, and each notification will then be treated as, oh, it's valid, oh, it's valid, oh, it's valid. And we keep making these idempotent changes at the back end, thinking all of these are valid, and suddenly our real-time metrics are off the charts, way off from where we were supposed to be. Of course, there are offline processing that we can do to be accurate, but we want to do this in real time. So the problem is we are overestimating campaign progress, as some of you might have already understood. And so for an example, let's go back to the same example. You have a goal of 100 impressions to show, and you get 100 notifications. And you assume that you've achieved the goals for the day, and you stop showing the ad. But the fact of the matter lies that you've actually received only 90 valid ones. 10 of these were duplicates, and these need not just be bots. Bots is just one thing which is easy to understand, but more so browser issues or mobile platform issues, anything that causes duplicate notifications to fire back to us and would result in invalid notifications. And that is called under-delivery, delivering less than what we would like. Well, how do we solve this now? Well, you just add a labeling mechanism which allows you to track in real time every notification that you're sending out so that you can know, oh, this is a notification, I am expecting this. Oh, this notification does not carry a valid ID. This is something I'm not expecting, and I discard it. And our new notification will now look like this. Of course, simplified version again. So you write to a store when you're making the bid, you get the win, you read from the store and validate whether this notification is indeed valid. And of course, you will have to remove it from the store once you get the valid win, because so that the next win, which is a duplicate, does not get validated again. Otherwise, all of this is pretty much pointless. And if you think about this closely, there would be residual IDs lying in, because every auction that you take part in, every bid that you make does not result in a win. So there will be some IDs which are just accumulating over time, which you need to purge, evict, remove. So we need some sort of mechanism for that. And now we realize how we have solved, or at least reduced, a very, very specific ad tech problem to something so general, and that is to find the appropriate key value store. And let's list down some requirements that we need to have in our key store. We need to handle requests at a scale, the scale that I was talking about earlier. and the ones that we will calculate the scale in the next slide, we need to be write optimized, because if you think about it, we are writing very often. We are writing every time we make a bit. But we are reading only when we get the notification, right? So this is very write optimized. It would be a good to have if our key store is optimized for small data sets, because we're just storing IDs. And we need a time-based eviction mechanism. We could have something like 30 minutes time TTL, but that would be overkill, because we mostly receive notification anywhere from 300 milliseconds to about a minute, but and sometimes up to like 3 to 5 minutes. 30 minutes definitely overkill, but captures all of the notifications that we want. Let's do some back of the envelope calculation. So I pull up this envelope and start writing. The total number of writes that I'll be making to this key store is equal to the total number of bids I'm making. Total number of reads will be equal to the wins that I'm making. So my total queries are basically the total number of bids plus the total number of wins, wins being overshadowed, so we can just deal with total number of bids. So we are looking at 20 billion bids, and this was back then in April, and we need 7 billion on a cluster. And so if we have one cluster of our key store on each of the data centers, we're looking at roughly 80K QPS. Nothing too fancy, but we still need something that can handle that scale. And something very interesting happened during this time. When I was trying to make these calculations, Redis came up with a big announcement, and I'm sure all of you heard that. Redis cluster no longer vaporware. This blog post by Antares made huge waves in the tech community, and this was me on October 14th trying to figure out if this is an appropriate key store. This is me on Stack Overflow asking some very, very basic questions about whether this will be good enough for what you're trying to accomplish. And this community is so great that just by a few online discussions, it was quite clear that Redis is the way to go. So I start prototyping. Let's build this. So we start with 2 physical machines and throw in 10 nodes per machine. Why 10 nodes? I don't know, it just felt good. 10 masters plus 10 slaves, because now we have a 20 node cluster. And no optimizations whatsoever, no configuration tweaking, no client-side optimizations, nothing. This is just, you put it in, and you're good to go, right? Because this is prototype. So now the bid flow is something like this. You make the bid, the auction is won, and you look in the key store, and 100 IDs can be time evicted by the TTL feature on every key basis. And as soon as we do that, we start seeing the numbers. So measure right after you build, right? And we see that anywhere from 1 to 5% of all the wins that we are receiving are duplicates or invalid. And that's huge correction for us if you consider the scale at which we operate, and our real-time metrics are so much better now. At Rocket Fuel, we are strong believers in being agile and keeping the feedback loop very short. So build something, iterate on it, and measure it, and then push in optimizations again. This way you keep the iteration loop short, and every iteration makes your product so much better. So let's start with a few observations. Of course, as noticed, plain sight, this is heavily write skewed. Writes are on a time-critical path, because as I said, each of these bids need to be responded within 100 milliseconds. And you're writing every time you're making a bid, so this is in your time-critical path, and you're waiting on Redis, not something you want to do. And reads can happen leisurely, because you do not have to respond to a notification that you are firing back to yourself. So this can take its time. So let's begin with some obvious optimizations. I'm sure all of you are already thinking ways to solve this. Well, the obvious one is to write to Redis in async mode. Your bidder thread is just concerned with making the bid. You separate concerns, have a separate thread pool which is responsible for writing to the store. Probably have a queue in between. And read will be in sync, because you can wait before updating your delivery management. A point I want to make over here is that if you think about it closely, we're making an assumption. Every time you do async, you need to think about it, right? Because it makes things so much faster, but it's definitely increasing complexity. And if you notice, the assumption we're making is that our write will complete before we get the notification. Is that a fair assumption? Well, you're writing within a data center, right? And as we see, the latencies are single millisecond latencies, single digit millisecond. But any notification to come back to us takes at least order of multiple 100 milliseconds. So I think we are fairly good with that assumption. So begins the next iteration again. Now we want to productionize this. So what do we need to do? We need to have some sort of a cluster management solution in place. You don't want to be getting up 11 p.m. or like 1 a.m. at night and just trying to fix, okay, which shard has been moved where. That should not be happening. And I had to do that when I was prototyping this, so that's not the way to go. Alerting and deployment need to be managed as well. You don't want your application to tell you that your Redis is running out of memory. You should have this in place. And to productionize this, you also need to consider every failure scenario now, of course, right? You need to consider what happens in the rare case of a complete cluster outage. Your Redis cluster is going to handle a few node failures for you, definitely. But what happens when there's a partition, big one, and your cluster is unavailable? What do you do? How does your application respond? Is it going to throw exceptions? So the optimizations that we went with were, of course, for deployment, we use Puppet, get everything on track. Nagios for alerting. Some of the common things we alert on are uptime, health check, memory, and latency values from the client side, right? And this is something I want to talk about for a little bit, the smart client feature. And by smart clients, I do not mean clients which can figure out which shard a key belongs to and which node contains that shard. But smart in the sense, can I contribute from my client side to handle failure scenarios? And apparently, yes, we can if you think a little outside the box. So your Redis is acting as a global key store in this solution. If each of these clients can actually store a little bit of that information at their end, then you have some sort of redundancy. You don't have to store all the data for 30 minutes. You can store something for like a minute, because most of your notifications will be coming back within a minute. From 300 milliseconds to 1 minute is where we see the most notifications come back. And if you just have 1 minute interval data, you're good for, I would say, 90% of all the reads that are going to be happening. So even in the rare case of a complete cluster outage, you have 90% availability. Isn't that cool? And now we were ready for production, and we productionized this, and we see some great numbers, and this performs well. And by performs well, I mean I built it, and it's working there, and I don't even know about it for like 2 months because it's just doing its job so well. But then when something succeeds so well, of course, it catches the attention, and you start thinking of what else can I do here. So this was a very simple get set kind of a thing, which is more convenient for a session like this. But then we started implementing increasingly complex services on this, list operations, huge lists, and an order of magnitude higher amount of reads. The proposed requirements were off the charts. We're looking at around 2 million operations per second. And there is a definite need now to optimize. We need to optimize on the total round trip times. And of course, memory, because now you're putting in so much data that your cluster may not scale, or you just are going to keep adding more and more machines. It's a possibility, but that's something which comes at a cost, I'm sure all of you know. So what do we do now? And I think if anyone wants to take anything away from today's talk, I think this slide is pretty much the slide. So we're looking at bigger cluster, but on the same number of machines. That's pretty interesting. And that is made possible because Redis, the way it works, is a single thread process. So you do not have to get a new machine every time you want a new process. And instead, to actually completely utilize all the cores on your machine, you would be better off having multiple instances running on a cluster mode. So that's what we did. We bumped this up. We got 2 tall machines with 40 cores roughly on each, 300 gigs of memory, and decided to build our cluster on top of these 2 tall machines. But still, the machines are still the 2. So with a cluster size of 160, we have ability to handle all of this traffic now that we're looking at. Another thing that we did was, this is a big decision to come to think of it, because you're saying, I don't want persistence. And saying that in a database is like, whoa. But this is a decision that is made possible because you have smart client-side enabled. You have clients which have some of the data, and you can use this to rebuild what you need. And if you think about it, you then can do away with a lot of disk features. And we are completely disk-free in all of our services. So no RDB, no AOF, and that has helped us get very low latencies. Remember I told you that a lot of the notifications come back to us within the first minute. And we have a 30-minute time period window for most of the keys. Now, this is one such optimization we can think of. Let's try to find a pattern within the keys on which keys are taking the most time. And if there is some sort of a platform where or let's say there's a pattern where, okay, if I show an ad to a mobile site or a video site, my notifications are going to come in late. If I have this kind of an understanding or a pattern, I can use that because at bid time, I know which platform I'm going to be serving my ad on and which ad I'm going to be serving. So using this information, I can set TTL, which is custom to the bid that is being made, and can reduce on the TTL. Lower TTL implies lower usage of memory overall, and that is very good. That is actually responsible for some of the dip that you see in the memory usage right in the 4th graph, remember? System tuning, this is a rabbit hole. You can go down in this all the way, optimize everything end to end. And what may be applicable to our cluster may not be applicable to your application and setup, but please look into what works for you. Do not go with defaults, especially, I would say, the way your client handles Redis cluster, maybe the pooling connections is something you should look at. Some of the things that helped us were ulimit values, maximum open file counts, SO max connections configuration, TCP timeout from the client side, and of course, THP, transparent huge pages. And these are just some of the things which I remember tweaking and tuning to get better performances from my Redis cluster. It also helps if all of your tunings and optimizations are leaning towards the same direction. And what I mean by that is if you have everything which is aligned towards tuning latencies, I can assure you that you're going to see some very astounding numbers as far as latencies are concerned. But of course, there is a trade-off, right? Because you enhance something, that will come at a cost. Is that cost acceptable to your application? Is a decision that you will have to make. This is something which is not very common in Redis. I want to talk about a problem which you can usually see at a much higher usage. What we have noticed is, let's say you have a cluster of 10 masters, 10 slaves, and you have one of the masters goes down. So there is something known as cluster node timeout setting within Redis. It's on the conf file settings. And after this interval of time elapses, the cluster decides that the slave needs to get promoted to this master, and you have your cluster running up and is handling queries within no time. What happens when this goes down? When the slave that got promoted and your master is still not back up? In that case, we've noticed that the cluster just fails according to the documentation and the specifications of Redis cluster. In that case, you have 2 choices, whether you want to continue writing, accessing this store, or do you want your application to realize this cluster failure and stop making requests to this cluster? And that is fine. That is a decision I'm sure all of you can make. But something weird happens when one of these nodes that has gone down comes back up and tries to get itself back into the cluster. This is something we've seen, I'm sure if you have been operating at this scale, you might have seen as well. We're not entirely sure of what is happening, but what you've seen is Redis cluster can sometimes freeze. And we have 2 tall boxes and all of them freeze. So basically your entire cluster is now in a stuck state. You cannot SSH into those boxes. And those are just some of the symptoms. We have Java threads which are trying to access this, and they get stuck. These are client threads. And basically affects our bidding for some time. And left by itself, it does not show any signs of recovery. We tried a few things. What seemed to work best for us was a back-off strategy. We start throttling our traffic as soon as we realize this. We start looking for symptoms about what may be happening, about when this happens, when our threads are spiking up really with high latencies. And then we start throttling our traffic from the client side and start reducing till the point where we see the latencies come back to original values. And then we start ramping it up again. This is something I just wanted to bring up because if you use it at that scale, you might face some problems which are very specific to your application. This is so huge. Lua scripting is such a big plus for Redis cluster that this itself could take a whole session. I'm surprised nobody has taken a whole session on Lua scripting because this reduced our total round trip times by an order of magnitude because now what you're doing is you're just sending one request to the server, and at the server you have a script, which is basically a custom command that you want to run, and that in itself is a series of commands, Redis commands. So now you're just one request to the Redis server is essentially making 3 or 5 operations and returning back to you. So what is the trade-off? Of course, here now you are increasing latency because now you have to perform so many operations, but you are saving so much on round-trip time. And all of those values which I mentioned earlier, round-trip time reminds me that the 95th and the 99th percentile values we were looking at are client-side values. So that includes the round-trip time. So finally, we've solved our problem, and how does a bid flow look like? We have a bid request, hits the bidder, we decide to make a bid. Just before making the bid, we decide to store this somewhere in Redis. And this is done in async mode. And you also write to the local client, right? As I mentioned, because this client comes into play when Redis cluster experiences a complete outage. So we write to something like a Java map with a TTL built in. In case the auction is won, we get the notification and we perform our magic. The bidder then looks for the unique ID of the notification, and if it's present in the Redis cluster, it assumes, right, that this is something I'm expecting and removes it from the store so that the next one that comes in will not be present. Of course, anything that has been tampered with will, of course, not be in our store to begin with. So that will not make its way to update real-time delivery management metrics. And only valid wins then go on to update the real-time metrics. And that brings me to the end of my talk. Some things that I want to summarize in the end are be empathetic to the requirements, not just of your application, but on the way your database works. If you're using Redis cluster, try to understand the configuration details. There's a lot of information online. Customize system tunings. You'll have to make a trade-off on how much time you want to spend tuning this, because you can keep tuning your systems to extract the last ounce of performance. Is that enough ROI for your developer time is a decision you will have to make, and the tech leads in your team will have to make. Keep trade-offs in mind when you're making any kind of optimizations. That's optimization 101. And avoid premature optimization. Sometimes you don't need to get the last ounce of performance, because that comes at a price. If nothing else, it is increasing your complexity. Probably my favorite summary point, iterate rapidly. because every iteration just makes your product so much better. Of course, we're hiring. Thank you.